right. Do you know what this is?
Rubber band.
Rubber band. And what kind of energy does it have?
Elastic.
Elastic. And what kind of energy is it? Is it potential or is it kinetic?
Potential.
Potential. So the energy lies in its stretched form, right? Right. So that's by virtue. So we, if you remember, we did something by virtue of its height, position. That was gravitational potential. Okay. This, the energy which is stored in a substance by virtue of the stretch. Okay. And that is called, we don't call it stretch. We call it configuration. So energy stored in an object because of its configuration is elastic energy, and that's potential energy too. So it's called elastic potential energy. You have gravitational potential energy and you have elastic potential energy. Have you ever had a spring toy?
Mm.
So this, what does spring do? It's like, it just like this, and then you compress it, and then it suddenly pushes the toy away, you know, like a jumping jack. So what is that energy in a spring?
Potential.
Potential. So that energy is also elastic potential energy. So in a rubber band or a spring, the energy stored is called elastic potential energy. Okay. Tell me something. One more question. So if I have to lift my phone up, now I am lifting it. So this is the ground level, and I'm lifting my phone up from here. Okay, I lift it up. And when I lift it up here, it has gravitational potential energy, right? When it was lying on the table, it does not have gravitational potential energy. When I lift it up to a height, now it has gravitational potential energy. How did I lift it up? What really did I do to lift it up to a height?
You did work.
I did work. So I did some work to lift the phone up. But what I'm doing is that I'm doing the work to transfer gravitational potential energy to this phone. Okay, so my hands are doing work to transfer gravitational potential energy to the phone. Okay, when we did this, when my hands did that work, two things happened. Can you tell me what are the two important things that would have happened?
Transfer energy.
Yes.
Energy conversion.
What happened to the position of the phone?
Change.
It changed. So it was at the ground level and then the position changed. Okay. Now this ruler that I have, this is a 30 centimeter long ruler. So I have lifted it up from the ground level to this height by 30 centimeter. Okay. So the word for that is when the object is moved from one position, from one point here, one point is the ground and the second point is this. When an object moves from one point to another, it is called displacement. All right. Now, if there is displacement in any kind of work done, displacement is an important factor. It has to change its position if I am doing work, if my hands are doing work. So earlier, I lifted it up to another height. Now I am pushing it. The phone was here at this end of the newspaper. Now I am pushing it. It's getting kinetic energy. So work is actually creating kinetic energy for the phone to move. And now the phone's position is the other end of the newspaper. From here to here, the phone moved. And when it moved, which means there was a change in position from this point to this point, and that was the displacement. Okay, so important factor in any work being done is displacement. The object on which the work is being done has to be displaced. There has to be a change in position for that object. That's one important factor when work is done. The second thing is, for me to do work, for me to lift this phone, can I do it without any force? Okay. I have to apply some force, right? Force is a pull or a push. You know that. Do you? Yes, have you done that before? So to do any kind of movement cannot happen without force. For any kind of movement, and movement is change in position. For any kind of movement, I have to apply force. So when I'm lifting it up, I am pulling the phone up. And when I was moving it from here to here, I was pushing the phone. Whether I am pulling or I am pushing, I am applying force. So for the work to be done, I have to also apply force. So force applied and the displacement, these are two important components for work to be done. And only when work is done can energy be created in an object. Okay. Energy transfer cannot, creation is a wrong word actually, because energy cannot be created, transfer. Only when work is done, energy can be transferred to an object. You have to do some work on the phone to make sure that energy is transferred to this phone. In this case, I transferred gravitational potential energy. And when I was moving it on the table, the work was done on the phone and I transferred kinetic energy to the phone. Okay. So it's extremely, extremely important concept, and it is very important that you understand this. Marissa, you have 1,000 questions you can ask me. We can do more examples. So tell me, do you understand this concept of how is work done? You do. Another thing you need to know is who is doing the work and on what object is the work being done. Okay. Now, if you look at this example, I am going to I have two objects over here. Okay, I am pushing the phone away. Now tell me, who is doing the work here?
You.
Okay, for a moment, imagine this is not my hand, this is some battery. This is a machine which is battery operated. Okay, for a moment, just imagine that. So tell me, who is doing the work? It's
That
this
object,
machine, right? It's this machine which is doing the work. And on whom is the work being done?
Your phone.
The phone. So the work is being done on the phone, but the work is done by this guy. These are two things you need to know to be able to understand the direction of the work. Which object is doing the work? and on which object is the work being done on which object is the energy being transferred in. So the energy was being transferred on this object and the work was done by this object. Okay, let's just do some theoretical work over here. Okay, so this is simple. Too important to, since you've written definitions also in your syllabus, that you need to know definitions of what is work, and you also need to solve some numericals of the formula. So this is really the definition, when a force acts upon an object to cause displacement of the object in the same direction, it is said that work was done upon the object. Now, if you look, I have been pushing the phone in this direction. So the force that is being applied is also in this direction, and the movement of the phone is also in this direction. They're both same, right? So work is done when force is applied to cause a displacement of an object in the same direction. Okay? That's the only time we can say force is done. In the opposite direction, it's called negative work. And I'll show you a couple of examples also how, when you apply the force in opposite direction, whether work is done or not done. And then you're going to have some situations in which you will think that you're doing work, but there is no displacement. So obviously then there is no work done. So we are going to look at a couple of more examples of that nature also. Yes. Okay. Okay. Here is how we can show directionally. You have a situation in which there is force being applied to this object. Okay. And the force is being applied in this direction. You see the arrowhead? In this direction, the force is being applied. When the force is applied in this direction, the object has moved from point A, say this was point A, to point B. Displacement is also in the same direction. So this is the case in which work is done. And when work is done like this, the formula that we use for work done is W is equal to force times displacement. In this case, F stands for force and S stands for displacement. Okay? And W stands for, of course, work done. Got it? The unit that we use for work done is, what is it? It's written on joules. Unit will be joules. Okay. Let's look at some of these examples, Marissa. This man's fishing out here. Can you tell me who is applying the force here on the fish?
The man.
The man. And what kind of force is he applying? Is he pulling or is he pushing?
Pull.
He's pulling. So the force applied is in upward direction, right? Now, is the fish going down or is the fish going up? Now, the force is being applied to the fish. Therefore, the work is also being done on the fish. Is the fish being displaced upwards or downwards?
Up.
Sorry, what?
Upwards.
Upwards. So the fish is also moving upwards. So tell me, in this case, is there work done or not?
Work is done. Yeah.
Work is done. The man has done work. What he did was he pulled the fish upwards. So the fish was displaced from wherever it was in the ocean to in the upward direction. All right. And it got some gravitational potential energy. Some gravitational potential energy got transferred to the fish. Okay. So like I said, you know what displacement is? Displacement is actually a distance between 2 points. And look at this. This guy is pushing the box. So he's pushing it in this direction, right? Am I right? Is this the direction he's pushing it in? And the box is being displaced in which direction?
In the same direction.
Same direction. So displacement is also happening in the same direction. Therefore, the work is done here as well. Okay? Now, in this case also, when you drop a ball and the ball falls down, why does the ball fall down?
Gravity.
Gravity. So who is doing the work on the ball here?
Earth.
Who is pulling the ball down?
Earth.
This boy is just left the ball, but the ball is being pulled by gravity. So who is doing the work?
The earth. Like.
If something falls down, that's falling down because gravity is pulling it down. So who is doing the work? Me or the gravity?
Oh, gravity.
Yeah. So gravity is doing the work in this case. So gravity is pulling the ball down. And so what would be the direction?
Down.
Downwards, and therefore the ball is going downwards. So that's your force, which is downwards. Okay. Now tell me, displacement of the ball. The ball was in the boy's hand. What is the displacement? Which direction is the displacement in?
Downwards.
Downwards again. So displacement is also in the same direction. So in this case also we can say work is done. But who did the work?
Gravity.
Gravity did the work. And on whom was the work done?
The ball.
The ball. And so what kind of energy was transferred by the work done by gravity?
gravitational potential energy
Really?
to
Are we raising the ball to a height or are we moving the ball?
move it. So
Moving.
kinetic.
Kinetic energy, absolutely right. Got it? So gravity did work on the ball and transferred kinetic energy. Are we clear? Are you understanding? So these are all examples that I've shown you in which the work is the displacement of the object is in the same direction as the direction of the force applied by the object which is doing the work. Okay. And in all such cases, it is very simple to calculate how much work is done. When the direction of the displacement and the direction of the force applied is same, we can use this simple formula to calculate how much work was done. And we'll do one such example now. What is this formula?
Work equals force times displacement.
Yes. Let's look at this man. What is he doing?
Lifting weights.
Yes. So imagine if the weights were kept on the floor, in which direction did he lift the weights up?
Up.
Upwards. So the displacement was upwards, right?
Mm.
And the force applied was also, did he pull or push?
Push.
Did he push? If I have to lift weights up, will I pull or push?
Pull.
Pull. So he pulled it up. So the force was also being applied in the upward direction. And imagine if these are weights. They are kept on the floor. Now I lift it up. I am applying force, and I applied force in the direction which was upwards. And the weights also moved in upward direction. So this is a clear case in which both the directions are same, and we can calculate work. Now, how much was the displacement here?
50. Displacement 2 meters.
2 meters. And how much is the force?
500 Newton.
Why 500 Newton?
50 kg.
Yeah. And you're multiplying with 10. Is that what you're doing?
I think my science teacher told us to measure it in Newton.
Yeah, that's fine. But are you multiplying 50 with 10?
Yes.
Okay. But you know that acceleration due to gravity is 9.8, right? Are you aware of that? It's only when you round it off, it becomes 10. Has your teacher asked you to multiply with 10 or 9.8?
10.
Okay, fine. Then we will keep it as 10 because I generally practice with all my students to multiply with 9.8. Then you get a more precise answer. But we'll go with what you're doing in school. All right, so your force is how many newtons? 500 newtons. Good. So now you know what the work done is. What is the work done?
500 times 2.
And that's?
1000.
What's the unit?
Joules.
Yeah. Always remember to mention the unit. Cool? Easy? Right? Okay, now we're going to use the same examples, Marissa. And we'll see there's something else also. You know, whenever there is some work being done, it's not always that there is only one force acting on it. There can be multiple forces acting on an object at the same time. Okay, if a car is moving, there is a force which is being applied by the thrust of the engine, but there is also a force which is applied by the friction on the road. Okay, if a balloon is up in the air, there is a force which is keeping it floating up. That is your, that's your friction. But there is a force which is also trying to pull it down, and that's gravity. So on any object at any given point of time, multiple forces are working on it. And we have to look at the object from the point of view of who is applying the force. We have to see who is applying the force, and then we need to check the object that is applying the force, is the work being done by that object or not. In this case, previously we saw that the man is doing the work because he is applying the force to pull it up. So he is doing work. But at the same time, there is another force which is at work. Can you tell me what that force is?
Pull.
So the man is applying the force in upward direction. So the fish went in upward direction. All right? But there is one parallel force which is working here, and I'm going to change that color to show you the distinction.
Gravity.
Gravity, absolutely right. So there is another force which wants the fish to fall down. It's just that the force that the man is applying is overpowering. It is more. And therefore, gravity is not winning. The man is winning. But not to say the force of gravity is not there. It is there. So the force of gravity is trying, it wants the fish to come down, but the man which has got the fishing rod is pulling it up. Okay, so this. Now tell me, if you think of it, all this while we were thinking of it from the perspective of the man. Is the man doing the work or not? Now let's think of it from the perspective of the gravity. What is the direction of the force applied by gravity?
Downwards.
Downwards. What is the direction of the displacement of the fish?
Upwards.
So it's opposite, right? In case of the displacement direction and the direction of the force, if they are in opposite directions, then the work done will always be negative, which is actually no work done. That's in physics, okay? So whenever the displacement, so in any situation, look at who is doing the work. Then decide whether the work being done is in opposite direction or same direction. You have to be able to clearly distinguish who is doing the work and on what is the work being done. The object on which the work is being done, the transfer of energy will happen on that object. Okay? Now this guy, the same example, we're looking at this boy pushing the box. The boy is pushing it in this direction, and the displacement is also in this direction. Here again, there is another force which is at play. Can you tell me which is that force?
Friction.
Absolutely right. And that's the frictional force. Frictional force always prevents the movement of an object, whether it is frictional force in the form of air resistance, or it's the frictional force between two surfaces. Here in this case, it's the floor and the box. Frictional force, the idea of friction is that I will stop the movement. I will not allow the movement. So if this guy is trying to push the box to create kinetic energy, to transfer kinetic energy, friction would want to stop it. So friction is applying the force on this box in the opposite direction. So what would the force be? Negative or positive? Sorry, what would the work be? Work done be negative or positive? By friction. Yes. So the work done by friction is negative here. All good so far? Let's look at this example. This is a porter who's got some luggage and he's moving forward. What is the position of the luggage here? Where is the luggage placed?
On his head.
On his head. Okay. He's got this luggage here. Now, he's lifting the luggage to keep it here. So the force applied is in which direction?
Upward.
Upwards. The force is being applied in the upward direction. As he is walking, is this box he's kept on the head also moving?
No.
No. The displacement has not happened. He might be applying upward force to keep the box on his head, but the box is not moving. So therefore, there is no displacement here at all. Okay. In such a case where there is no displacement at all of the object on which the work is being, or supposedly the force is being applied, then is there any work done? Because for work to be done, two conditions are important, and those two conditions are force and displacement. Here, the only one condition that was met was force. The second condition of displacement did not happen with this box. So the force being done over here is 0. All right? Now you're going to tell me here. Let's look at these pictures. And you're going to tell me if the work is being done or not by this girl. All right? Tell me what's happening in the first one. Is the work being done or not?
Yeah.
Okay. So let's write yes here. What about the second one?
No.
Why no?
It's not in the same direction.
Okay. So the force is being applied in upward direction.
Yeah.
And the bag continues to be on her shoulder. So that there is no displacement at all for the bag, right?
Oh,
That's why.
yeah.
Okay, let's look at the next one.
Yes.
Yes. Why? Because she's lifting it up. So force is upwards, and the bag also from the floor level will move up. So yes, here. Tell me the next one.
No.
No. Once again, why?
The direction of force is upwards, but the bag
Is in
isn't
her.
moving.
Yeah.
So there's no display.
There is no displacement. Fantastic. And we are right. These are the correct answers. Okay. Tell me here. You remember this scene from Thanos, do you? Captain Marvel, she was pushing Thanos's hand, but it wasn't quite moving. So tell me, did Captain Marvel do some work?
No.
No. Absolutely right. Poor Captain Marvel. After applying so much work, there was no work done. Anyway, so that's where now you understand how it works. So we're going to do this worksheet now. So I'm going to start off with some very, very simple problems, Marissa, and then we'll go on to gravitational potential. Okay. Now you got to tell me if, so I've taken out some very simple problems, but if you think your teachers give you more complex problems, then I'm going to make you practice more complex problems. You know, I don't want to take you to a level which you're not doing in your class. So it'll be a good idea for you to even share some of the problems that your teacher, or some of your homeworks which your teacher is given, because that will give me an idea of the complexity of problems that your teachers give. Okay. Accordingly, I can make you practice. So these are some simple ones. All right, look at this problem, read and tell me what's the answer.
Two.
So
2 joules.
yeah, 2 joules. Does your teacher insist on writing the steps in any numerical?
Yeah.
So you're going to do that. So you're going to tell me what's the force?
Force equals to 1 Newton.
Yeah, 1 Newton. Then you're going to write what's the displacement? 2 meters.
2 meters.
What's the formula?
F times force times displacement.
Yes. And so you will apply, which will be 1 times 2. This is as simple as we can get. And you will always write the units. All right. So whenever you're doing the problem, please do follow the steps, because at least I know that when I'm marking my students, if they don't write the steps, they don't get full marks. Okay, and I'm sure your teachers might be doing the same. Let's look at the second one, Marissa. Simple.
The force is 15 newtons.
Yes.
And the displacement is 3 meters. Since work done equals force times displacement,
Yes.
it is 15 newtons times 3,
Yeah.
which is 45 joules.
Right. Let's go down further. Okay.
Mm,
Do you want to use annotation and just do the problem here?
uh,
You can actually annotate.
okay. I annotate.
Yeah, you can.
Okay. Wait, no.
Yeah. What happened?
Hmm?
You're right.
Wait. Cos x 15. Mm, hmm?
Yeah.
What's
We need
this?
to find out force.
This work done.
Yeah.
And force equals 50 divided by 5, 10 Newton.
Awesome. Let's go down. You can erase this. Let's do this.
Which one?
Fourth one?
Okay, wait. Hmm? Ah,
What are you doing?
work done equals 150 joules. So displacement equals 150 divided by 100 equals 1.5 joule. Meters.
Yeah. You can again get rid of that. Okay, tell me the sixth one.
Mm, force equals 9,000. Oh wait, no. Then there was no work done.
There was no work done. This was a trick question. All right. Okay, let me see if I can get you to do one more problem, and then after that we'll move to gravitational potential energy. Okay, this is, let's see. Try and attempt this one. The eighth one.
What work is done?
Nice, very good. Are you allowed calculators in school?
Yeah.
You are?
Mm,
Right now, were you using a calculator or was this mental math?
calculator.
And I was thinking, you know, your mental math is so fast. Thanks for your honesty. Okay. All right, so I will send you a couple of more problems to do on work. But right now in today's class, we are going to move to gravitational potential energy calculation now. Okay, is work clear, Marissa?
Yeah, but the questions that my teacher gave out like a lot more confusing.
So that's exactly what I wanted to know. If I can give you more complex questions, but I just wanted to know exactly what level of complexity are you really, what kind of problems you're doing in school. So one sample homework, or maybe a couple of problems that you find very difficult, that you found difficult when you were doing this unit in your school, if you send it to me, I will know exactly what kind of problems to have you practice. Then I can do that in the next class. Okay?
Okay.
All right. Okay, just give me a moment. So you know the formula of gravitational potential energy. What's the formula of gravitational potential energy? I didn't teach you, but I'm assuming you would know.
MGH?
Yes, MGH. That's right. What are the two important factors? Just like the way when we were doing work done, we said there are two very important factors that are important to consider when you are talking about work done, and that's displacement, and the second one is force. Similarly, there are two very, very important factors which can change the gravitational potential energy. It can either increase the gravitational potential energy or it can decrease the gravitational potential energy. What are those two factors? So we'll talk a little about that. Okay, imagine you have a tennis ball and you have a football. Okay. If you were to drop both of these from first floor of a building, which one do you think will have more gravitational potential energy? Which one do you think is going to do more damage when it drops? Football. Because it was more massive than the tennis ball, right? The mass of the football was much more than that of the tennis ball. So mass of an object is extremely important and it determines how much gravitational potential energy an object stores. If the mass is smaller, the GPE will be less. GPE is gravitational potential energy. And if the mass is higher, the gravitational potential energy also will be higher, right? The second factor which determines gravitational potential energy is the height. Now, if you were to use the same tennis ball and drop it from 15th floor versus if you were dropping the same ball from first floor, when will it cause more damage?
15th floor.
15th floor. So more the height, higher the ball was, higher was the gravitational potential energy stored in the ball. And lower the height, lesser is the gravitational potential energy. So both mass and height are important factors which tell us how much GPE there is in an object. More mass, more height, that means more GPE. Less mass, less height, less GPE. So we are going to use the formula that you just said, mgh, wherein G stands for, what does G stand for? Come on. Acceleration due to gravity. G stands for acceleration due to gravity. The same number, 9.8 meters per second square, which of course in your school, you've been rounding it off to 10 meters per second square, right? What are the units we use here? What are the standard units we use here? Let's look at the standard units. The units are very important, Marissa. Always know these standard units in every numerical. So when we are calculating gravitational potential energy, your standard units for, and this is a common mistake that all students make, because they understand that the standard unit of mass is always grams. So that's what they think, even that's the unit they're supposed to use here also, but no. When you're doing any calculation for gravitational potential energy, the standard unit considered is always kilograms. It is never grams. So if you get a problem which is giving information of the mass in grams, convert it to kilograms. Okay, so mass will always be in kilograms. Your acceleration due to gravity, you will take this as 10 meters per second square. Remember, this is per second square. Okay, and your height will be always in meters. So when you calculate GPE, which is mgh, the unit will be, GPE unit will be always joules. All right. Shall we do some numericals, some problems for calculation of GPE? Are you feeling tired?
A bit.
A bit? There's no problem. In any case, it's 6:27. I can always do these problems with you in the next class. So in the next class, we will do GPE calculation. We will also do kinetic energy calculation. And then we will try and mix these formulae in which, we'll try and do numericals in which you will need to use more than two formulae. Maybe you will need to first calculate the work done, or you may need to calculate the displacement, and then you need to calculate the GPE, or you may need to calculate the mass first and then the kinetic energy. So we'll try and integrate these formulae and do a couple of more complex problems. So next class, we will only focus on numericals. Okay. Do you have any questions so far? No? That's good then. Okay, I won't teach you anything. Can you maybe share screen and show me a few, some of the work that you've done in school?
I don't have it on my iPad, but I have the hard copy.
Just show it to me like this. Or you can take a picture and mail it to me.
For work, right?
Yeah. Work, GPE, kinetic energy. Okay.
Then there's
Okay.
then it's like got graph. There's a graph.
Okay. Okay. So send me pictures of these worksheets then. All right.
Okay.
All right.
Now
We can say bye-bye for today. If you have any questions, you can ask me right now.
question.
No questions. Okay. Have a lovely weekend, a restful weekend. Bye. Good night.
Bye bye. Night.